Assalamu alaikum. My name is Safa Ali and I'm a student of the Biochemistry BS. As you know, the previous students asked you about the NMR introduction and NMR interruptions and the principles. My part is NMR chemical shift and NMR spectroscopy techniques. Let's ask about the NMR chemical shift. First is about the magnetic field. A spinning charge generates a magnetic field that results in a magnetic moment proportional to the spin. In the presence of the external magnetic field, two spin states exist, one spin up and one spin down, where one aligns with the magnetic field and the other opposes it. The next point is about the energy difference. The difference in the energy del E between the two spin states increases as the strength of the field increases. But this difference is usually very small, leading to the requirement for the strong NMR magnets. Irradiation of a sample with the energy corresponds to the exact spin state separation of the specific set nuclei will cause excitation of those set of the nuclei in the lower energy state to the high energy state. The about absorption of the RF energy. This difference arises from the differing electronic environments of the nucleus of the interest. Upon application of the external magnetic field, these electrons move in response to the field. These electrons move in response to the field and generate the local magnetic fields that oppose the much stronger applied field. This local field thus shields the proton from the applied magnetic fields, which must therefore be increased in order to achieve the resonance absorption of the RF energy. Such increments are very small, usually in the parts per million. The example of a proton peak from the aldehyde. Um, since an electron withdrawing group, the carbonyl de-shields the proton by reducing the local electron density. The difference between the 2.34780 and 2.3478 is therefore about the 42 parts per million. However, a frequency scale is commonly used to designate the NMR signals, even though spectrometer may operate by sweeping the magnetic field, and thus the 42 parts per million is about the 4200 Hz for a 100 MHz reference frequency RF. The next point is about the NMR, the signals. The NMR signals location of a different is dependent on the external magnetic field. Okay, and the signals are usually reported relative to a reference signal. Additionally, since the distribution of the NMR signals is field dependent, these frequencies are divided by the spectrometer frequency. The next part of my is about the chemical shift. The units of the chemical shifts are the parts per million, and the however, since we are dividing the hertz by the megahertz, the resulting number would be too small. Thus, it is multiplied by a million. This operation therefore gives a locator number called as the chemical shift. Okay. And the example of the chemical shift of a proton. For the protons are highly predictable since the shifts are primarily determined by the simpler shielding effect. But the chemical shifts for many heavier nuclei are more strongly influenced by the other factors, including the excited states. For example, the H1 NMR spectrum from the ethanol 1 would accept the signals at each of the specific chemical shifts. At each of the specific chemical shifts, one for the CH3 group, one for the CH2 group, and one for the OH group. A typical CH3 group has a shift around the 1 parts per million. A CH2 attached to an OH and has a shift around of the 4 parts per million, and OH has a shift where from the 2 to 6 parts per million depending on the solvent used and the amount of the hydrogen bonding. Okay. The next my point is about the paramagnetic NMR spectroscopy. The paramagnetic NMR spectroscopy measurements are conducted on the paramagnetic samples. The paramagnetism gives rise to diverse chemical shifts in H1 NMR spectroscopy. The chemical shift range up to thousands of the parts per million. Okay. This is an example of the hexaborane B6H10. The next point is about the analysis of the signal intensity, which under conditions of the optimal relaxation correlate with the number of the protons that of the type. Analysis of the signal by the integration, the mathematical process that calculates area under a curve. The analyst must integrate the peak and not measure its height, but the peaks also with, and its size is dependent on its area and not its height. However, it should be mentioned that the number of the protons or any other observed nucleus is only proportional to the intensity or the integral of the NMR signal. For instance, experiments typically used to obtain the carbon-13 NMR spectra. The integral of the signals depends on the relaxation rate of the nucleus and its scalar dipolar coupling constants. Very often these factors are very poorly known, therefore the integral of the NMR signal is very difficult to interpret in more complicated NMR experiments. The next and my very important point is about the J coupling. A very special case of the spin-spin coupling between the NMR active nuclei. This coupling arises from the interaction of the different spin states through the chemical bonds of the molecules and results in the splitting of the NMR signals. For a proton, the local magnetic field is slightly different depending on whether an adjacent nucleus points towards or against the spectrometer magnetic field, which gives rise to the two signals per proton instead of the one. These splitting patterns can be complex or simple and likewise can be straightforwardly interrupted by the deceptive. And for the example of the J coupling is about the proton spectrum for the ethanol described above as CH2 group is split into a triplet with an intensity ratio of the 1:2:1 by the two neighboring CH2 protons. The next important and point is about the second order coupling. It is a strong coupling. If the shift separation decreases, the multiple intensity patterns are first distorted and they become more complex and less easily analyzed. If more than two spins are involved, especially intensification of some peaks in a multiplet is achieved at the expense of the remainder, which sometimes almost disappear in the background noise. Although the integrated area under the peaks remains constant in most high field NMR, however, the distortions are usually modest and the characteristic roofing can it help to identify the related peaks. And the last my point is about the chemical shifts and on the magnetic inequivalence. More subtle effects can occur if chemical equivalent spins symmetry, and so having the same NMR have different coupling relationships to the external spins. For example, the four hydrogen sides of the 1,2,2-dechlorobenzene divided into two chemical equivalent pairs by this symmetry, but an individual member of one of the pairs had different couplings to a spin making up the one pair. Magnetic inequivalence can lead to high complex spectra which can only be analyzed by the computational modeling. Such effects are more common in the NMR spectra of the aromatic and the other non-flexible systems, while conformational average about the C bonds in the flexible molecules tends to equalize the couplings between the protons on the adjacent carbons, and it reducing the problems with the magnetic inequivalence. Move to next the slide. The NMR basic spectroscopy techniques. Okay. The first technique is about the resonant frequency. The resonant frequency, energy of the radiation absorbed, and the intensity of the signal are proportional to the strength of the magnetic field. For example, 121 Tesla magnetic field, hydrogen nuclei, commonly referred to as protons, resonate at 900 MHz. It is common to refer to 21 Tesla magnet as a 900 MHz. Magnet, since hydrogen is the most common nucleus detected. However, different nuclei will resonate at different frequencies, and the field strength in the proportion to their nuclear magnet moments. The next important technique is about the sample handling. An NMR spectroscopy typically consists of a spinning sample holder inside a very strong magnet, a radio frequency emitter, and a receiver with a probe. Spinning the sample is usually necessary to average out the diffusional motion. However, some experiments call for stationary sample when the solution movements is an important variable. For example, the measurements of the diffusion constants are done using the stationary sample with a spinning off, and flow cells can be used for online analysis of the process flows. The third technique is the diuretic solvents. The vast majority of the new molecules in a solution are the solvent molecules, and the regular solvents are the hydrocarbons and contains the NMR active protons. The most widely used diuretic solvent is diurochloroform CDCl3. All the other solvents may be used for the various reasons. Such solubility of the sample desire to control the hydrogen bonding. The chemical shifts of a molecule will change slightly between the solvents, and the solvent used will almost always be reported with the chemical shifts. The NMR spectra are often calibrated against the known solvent residual proton peak instead of the added tetramethylsilane. Okay. The fourth technique is shim and log. To detect the very small frequency shifts due to the nuclear magnetic resonance NMR, the applied magnetic field must be constant throughout the sample volume. Okay. High resolution NMR spectrometers are shims use the shims to adjust the homogeneity of the magnetic field to the parts per billion. In order to detect the compensate for the inhomogeneity and the drift in the magnetic field, the spectrometer maintains a lock on the solvent neutron frequency with a separate lock unit, which is essentially an additional transmitter and RF processor tuned to the lock nucleus. In the modern NMR spectrometers, shimming is adjusted automatically through, in some cases, operator has to optimize the shim parameters manually to obtain the best possible resolution. Move on to the next. The last part of my presentation is about the acquisition of the spectra. Okay. Upon the excitation of the sample with a radio frequency pulse, a nuclear magnetic resonance response, a free induction decay FID is obtained. It is a very weak signal and requires sensitive radio receivers to pick up. A Fourier transform is carried out to extract the frequency domain spectrum from the raw time domain FID. A spectrum from a signal FID has a low signal to noise ratio, but it improves readily with an averaging of repeated acquisitions. Example, H1 NMR spectra can be acquired with the 16 repeats with the takes only minutes. However, elements have the heavier than the hydrogen, the relaxation time is rather longer, around the 8 seconds for 13 carbon. The acquisition of the quantitative heavy element spectra can be time consuming, taking the 10 minutes to hours. So this is the my concept. I hope your points are clear now, and thank you so much. Allah Hafiz.